This is the fourth in a 7-video series about hypothesis testing, one standard deviation. Let's examine a claim about a standard deviation. Suppose we were to claim that the standard deviation of heights of people is less than 3 inches. And we want to test this claim with a significance of 5%. Well, what does that mean? Well, it has to do with a false positive. Here's an example. Suppose we were to do a study and find a sample standard deviation that was well below 3, say 2 inches or 1.8 inches or something like that. Could that low of a standard deviation in the sample just be a complete statistical accident? Could it have happened by chance even if the claim here were not true? Well, there are cases where that happens, and we call that a false positive. So when we say we want to test the claim with 5% significance, we're saying that we're willing to accept up to a 5% chance that a result that we have that appears to prove the claim might have happened by chance or might be a false positive. Okay, so here's some sample data. 18 people's heights are measured, and suppose the sample standard deviation for those 18 people was 2.2 inches. We call that S. Now in our 5 steps for hypothesis testing, we immediately start in step 3 because assuming you're a student in a statistics class, steps 1 and 2 have been done for you. The claim has been made, the significance has been stated, and the gathering of random samples has been done and stated for you in the problem. So we're going to start with step 3, which is really step 1 for us, the mindset of assuming equality. And that's where you assume something that is contrary to what it is we're trying to prove. We're trying to prove that the standard deviation of heights is less than 3. We're going to assume to the contrary that it is exactly 3. And why do we do this? Well, because this so-called null hypothesis, the assumption that runs contrary to what we're trying to prove, if we can assume that and look at our sample data and deduce that it probably couldn't have happened by chance, then that will cast a shadow of doubt on the null hypothesis, and that might lead us to accept our original assertion in green that the standard deviation is less than 3 inches. So in this mindset of equality, let's examine a sampling distribution. Now, you've probably seen sampling distributions before for means and proportions, and they tend to be a bell curve. But the sampling distribution for standard deviations is slightly different. It has a similar shape, but it's skewed to the right. And we call this a chi-square distribution. And this calculation here, n minus 1 times s squared over sigma squared, is referred to the chi-square quantity. Now just to give you a sense of what this distribution means, or what I mean when I put this distribution here, suppose that we were to repeatedly over and over sample 18 people, and each time we recorded the sample standard deviation. Now assume we were doing this in a population whose standard deviation was 3, and we did this repeatedly. We would get this kind of distribution of all of these calculations. Let me say that another way. In this formula here, if we were to plug in n equals 18, which is the number of people sampled, and sigma equals 3, the assumed population standard deviation, at least as far as the null hypothesis goes, but if every time we did a sample of 18 people, we got a different s value, so not just the 2.2 shown above, But if every time we did this, we took our S value and plugged it into this expression here, we would get a different so-called chi-square value each time. And if we did that many, many, many times, we would get a distribution that looks like this. And now the question is, if we plug 2.2 into this expression, are we going to get something significantly low enough for us to be able to support the claim that the standard deviation is actually less than 3 inches? Well, to find that out, we're going to find the probability of getting a sample standard deviation as low as 2.2. Now, when your claim is regarding a standard deviation, unlike what you may have seen in previous videos, the standard error isn't relevant, and we compute what's called our chi-squared test statistic, as I mentioned earlier. That funny little Greek letter that looks like an X is the Greek letter chi, just so you know. And we're going to use this chi-squared distribution and a function called chi-squared cumulative distribution function, or chi-squared CDF, to compute this. Now, we'll do one of these two chi-square CDF calculations, and here's where it would depend on the type of the claim. If you look at the claim in green, you'll notice it says that something is less than a certain number. When you're doing a less than claim, as we are here, you use the top one of these two formulas. So I'll take that one out of there for now. And let's go on to our specific calculation. Since we sampled 18 people, n minus 1 is 17, plugging in the 2.2 and the 3 into the chi-square formula gives us a value of 9.1-ish. Now, this doesn't have any particular meaning other than it gets fed into the chi-squared cumulative distribution function. And also notice my degrees of freedom are 17, one less than the number of samples. And when you do this on a calculator or other software, you get a probability value of 0.064, And what does this mean? It means that if the null hypothesis were true, the probability of getting a sample standard deviation as low as we did, 2.2, is only 6.4%. Now that's not very likely, and so it's unlikely that we have gotten this sample standard deviation by chance, but when it comes to drawing our conclusion, we have to remember that our original stated significance was 5%. We agreed at the start of this problem, or it was stated in the problem from a student's perspective, that if the probability of a false positive was anywhere up to 5%, we would accept the claim. But we have a 6.4% probability of this being a false positive, and therefore we did not reach the level that we had set for ourselves in order to accept the claim. And since 6.4 is bigger than 5, there is not enough evidence to support the claim that the standard deviation of heights is less than 3. Now, might it be less than 3 despite our lack of evidence? Absolutely. We're not saying that the claim is wrong. We're saying that there isn't enough evidence to support the claim based on the statistical sample data that we collected. Let's look at another problem. Suppose we were to claim that the standard deviation of lung volumes is more than 200 milliliters. Lung volume is how much air a person can hold in their lungs at any given moment. By the way, just as a side note, the average lung size is about 5 liters or 5,000 milliliters, but here we're talking about a standard deviation. So the claim is that the standard deviation is more than 200. And we want to test this claim with a 2% significance. Now, that's a pretty high threshold, That means unless the probability of a type 1 error or false positive is less than 2%, we're not going to be able to claim enough evidence to support what we're trying to support here. And that's the meaning of that. So our sample data contains 40 patients. And among those 40 patients, the sample standard deviation was 247 milliliters. Now the claim we're trying to prove is that the population standard deviation is more than 200. Well, the sample standard deviation is clearly more than 200, but of course the question is that enough to prove it at this level of 2% significance? Okay, so on to step 3, which is really our first step if we're statistics students in a classroom. We're going to assume that the population standard deviation is exactly 200. Why? Because if we assume this null hypothesis and we find out that our sample data is highly unlikely to have occurred by chance, then that will make us reject the null hypothesis and accept the alternative hypothesis that we're trying to prove. Now let's again look at our chi-squared sampling distribution, which looks like a normal distribution but is skewed to the right. If this 247, when plugged into this formula, gives us a chi-squared value that's significantly large, then that will prove the claim that the standard deviation of lung volumes is more than 200 milliliters. So let's get to the probability calculation. Again, when your claim is regarding a standard deviation, the so-called standard error isn't relevant. Our test statistic and the chi-square distribution, along with one of these two, will give us the probability. Now, out of the two formulas on the right, we are going to use the bottom one in this case, because if you notice the claim typed in green, the claim is that a standard deviation is more than a certain number, and whenever you have a more than claim, you use the bottom of these two formulas. So I'll get rid of that one. So, plugging in all of the normal calculations, we had 40 patients, so n-1 is 39. Plugging in the sample and assumed population standard deviations gives us a chi-squared value of 59-ish. And plugging that number into chi-square CDF ultimately gives us a probability of 1.9%. And what that means is that there's only a 1.9% chance that our sample standard deviation was this high by chance. And since our conclusion is based on our significance, and since 1.9 is less than 2%, we've met the threshold of proof to state that since 1.9 is less than 2, there is in fact sufficient evidence to support this claim that the standard deviation of lung volumes is greater than 200 milliliters. And that completes lesson 4 of 7.